This video will cover Chapter 6, Section 1. We're going to focus on understanding what continuous probability distributions are. We're going to focus in this video on the normal distribution, talk about what the standard normal distribution is, and determine probabilities using the standard normal distribution and normdist in Excel. As we've talked about before, a continuous random variable is a variable that can take on infinitely many values, or an uncountable number of values. So examples are a thickness of an item, the time required to complete a task. This continuous random variable could take on any value depending on our ability to accurately measure this data. For Chapter 6, we're only going to talk about two kinds of continuous distributions, the normal distribution and the uniform distribution. And there's something different here than what we did when we were looking at discrete distributions. For discrete distributions, we could talk about the probability of an individual value. For continuous distributions, we talk about the probability of a range of values instead of a single value. So some range of values from A to B, what's the probability of the random variable taking on the values in the interval between A and B? The normal distribution is this bell-shaped distribution. The distribution is symmetric about the mean, which means the left-hand side around the mean looks like the right-hand side around the mean. The mean equals the median equals the mode. We actually call this unimodal because there's only one mode, one high point in the curve. The location of this distribution, where it sits on the x-axis, is determined by the mean. The spread of this distribution is determined by the standard deviation. How fat this curve is determined by that standard deviation. The values theoretically go from negative infinity all the way up to positive infinity. The book gives you this formula, f of x equals 1 over the standard deviation times the square root of all this stuff. And you might be trying to figure out what that equation is and how we're going to use it. Well, we're not actually going to use it directly. But this actually tells us the height of this normal distribution at each possible value for x. So it's truly the function that defines this normal distribution curve. There are actually infinitely many normal probability distributions. Those distributions depend on mu and sigma. If we change mu, we get a new normal distribution. If we change sigma, we get a different normal distribution. So this picture on the left actually shows three normal distributions. The first one has a relatively small mean and a small standard deviation. Notice that the curve is kind of close to the mean. The second distribution shows a higher mean and a higher standard deviation. So we notice the mean is further to the right on the x-axis and the curve is shorter and fatter. And the third distribution shows an even higher standard deviation and mean, a shorter, fatter curve that sits even higher up on the x-axis. The total area under the normal probability distribution curve has to add up to be 1, just like all of the other probability distributions that we've already talked about. Because this curve is symmetric, we know that half of the probability is to the left of the mean. So the probability of being less than the mean, or between negative infinity and the mean, is 1/2. The probability of being above the mean, between the mean and positive infinity, is also 1/2. For continuous probability distributions, there are infinitely many possible values. So the probability of any particular value occurring is actually 0. So that's why we have to talk about finding the probability of a range of values. These values could be something like A to B. These are values of x on that x-axis. We want to find the probability of being between A and B. That's the area under the curve between those two values. Now, to find probabilities for the normal distribution, we have historically always used this thing called the standard normal distribution. This is a distribution that has a mean of 0 and a standard deviation of 1. The horizontal axis is the z-axis instead of the x-axis, where z is actually just the number of standard deviations, and x value would be away from the mean. If the x values are above the mean, we will get positive z values associated with that. If the x values are below the mean, we will have negative z values. So we've used this formula before. This is the formula for standardizing a data point. In other words, turning it into how many standard deviations away from the mean is that individual data point. The picture below is actually the standard normal distribution. The standard normal is centered at 0 because the mean is 0 standard deviations away from the mean. The standard deviation here is actually 1 because a value that is 1 standard deviation away from the mean will generate a z-score of 1. Any normal distribution can be scaled into a standard normal distribution, and any individual value of x can be scaled into a z-value. We can use these z-values and the standard normal distribution to find probabilities. Just as a reminder, this is an example of how we convert an x value into a z-value. So assume that x comes from a distribution that's distributed normally. The mean of that distribution is 100 and the standard deviation of 50. The z-value for 250 is 250 minus 100 divided by 50, or 150, that's the deviation, divided by 50, which is 3. That means that 250 is 3 standard deviations above the mean of 100. Here's a picture to represent that same thing. We see this normal distribution centered at 100 with a standard deviation of 50. In z terms, that 100 is actually 0 because 100 is the mean. It's no standard deviations away from itself. 250 is 3 standard deviations above the mean. There are 3 ways that we can find probabilities. The book provides you a standard normal table in Appendix D. This table focuses on probabilities between individual values of z and the mean of the distribution. I'm going to provide you a table. I'm going to call it Wendy's version. It's a standard normal table also, but it reads a little bit differently. This table focuses on all the area to the left of the individual z value that we're looking at. And actually, this table thinks the same way as the function in Excel called normDist. NormDist also calculates the area to the left of the value entered into the function. So the book's standard normal table is in Appendix D. It gives us the probability between the mean and some x value that we're interested in. So I put here, it gives the probability from the mean of the distribution, that would be a z-score of 0, up to a desired z-score, which is really the converted value of x. So it could give us something like this, the probability of being between the mean and 2 standard deviations above the mean. For an example of this, pretend that the mean is 8 and the standard deviation is 5. Suppose that we want to find the probability of being between the mean of 8 and the value of 8.6. So we know that 8 is the mean, so we're looking between the mean and how many standard deviations above the mean. I know it's above the mean because it's 8.6. So 8.6 minus 8 divided by 5 gives us 0.12. So 8.6 is 0.12 standard deviations above the mean. So I've taken the x values and converted them into z values. The table from the book will provide us this probability of being between 0 and 1.2. So if I go to the table from the book, I go down to 0.1 and across until I get to the hundredths place of 2. So 0.12, the probability is 4.78%, or 0.0478. Now this is fine and works really well if you're interested in the probability between the mean and a particular value. But for probabilities that are not between the mean and a given value of x, we would have to add 0.5 or subtract from 0.5 or maybe do some other kind of combination of things to get the probability of interest. So sometimes for me that can be a little bit confusing. So I like the probability distribution for the standard normal that actually looks from the left of the value that you're interested in. And what it's going to do is calculate the probability from negative infinity up to the desired z-score, which is really our converted value of x. So that probability table actually shows us the probability to the left of the number of interest. So suppose we were interested in the probability of being less than 2 standard deviations above the mean. Well, that's all the probability to the left of 2.0. My table that I'm going to show you will do that. it's going to give us the value of 0.9772 if we want to be less than or equal to 2 standard deviations above the mean. So again, an example, suppose that we're interested in the probability of being less than 8.6 given that mean of 8 and the standard deviation of 5. We're going to calculate that z-score again, and it's the same z-score. 8.6 is 0.12 standard deviations above the mean. My table looks to the left of that 0.12 and calculates all the probability of being to the left of 0.12. So we go to the table and read it the same way. We go down to 0.1 and over to the hundredths place of 2, so we get 0.12 that way, and read down and in. We find the probability of being to the left of 8.6 being 0.5478, or 54.78%. Now this works really well if we're interested in the probability to the left of a number. But if we're interested in the probability to the right of the number, we are going to have to subtract from 1. And if we're interested in the probability between two numbers, we're going to have to subtract those two probabilities from each other. Excel actually thinks the same way as Wendy's version of the table. It's going to find the probability of being to the left of some x value when x is normally distributed. So when I do a problem like this, I start out by drawing the normal curve for the problem in terms of x. So I've drawn my x-axis here, put my bell curve on it, and I'm looking at the probability of being to the left of some data value. Norm dist will allow us to do this. The x value of interest goes into the x box here, so we'd type in 8.6. The mean and the standard deviation are the mean and standard deviation of the distribution. So the mean of our distribution is 8. It would go in the mean box here. We would type in 8. The standard deviation was 5. So we would type 5 into the standard deviation box. And cumulative, I've noted here, is true. For norm dist, cumulative will always be true. When we click into cumulative here, it asks us if we want to add up all the values to the left or if we want to just have the value at that particular point. If we put false in here, we actually get the value that indicates the height of this curve. We don't care about the height of the curve. We care about the area underneath the curve. We want to add up all that area to the left of the data value that we've entered. So if we enter cumulative as true, then we're always going to get that area to the left of the data value that we're interested in. So the general process for finding probabilities from a normal distribution. First, make sure you know what the mean and the standard deviation are. Then define your event of interest. So I put here the probability of x being greater than some x value as an example. And draw a picture. So I always start by drawing my x-axis, making a bell curve, and it doesn't have to be perfect. We're just trying to get an idea of what this looks like. Put in the mean and then our value of interest and shade in the probability that we're trying to find. So this would be an example of trying to find a probability of greater than A given our mean and whatever the standard deviation is of this distribution. If you want to use the table, the third step would be to convert the x value into the standard normal value, the z value, and use the table to find your probability. If you're interested in using norm dist instead, you do not need to convert your x value into a z-score. You can enter the x, mean, and standard deviation directly into norm dist in Excel.